Okay, welcome back to a new origin tutorial. In this video I would like to explain how you can create a histogram, and in this case we use Gaussian distributed data which I have randomly generated before. And then after creating this histogram, how you can make a Gaussian fit to that, which is a typical situation in physics where you have done any measurement and you can expect that maybe the measurement data that you have is somehow Gaussian distributed. So it's also, or it would make sense to also know how to make a fit to that. So here we have this data that I have created before, and this I have done actually with root. So these are 100,000 measurement points, and all of them are distributed around the value of 5 with a sigma value of 0.5. And here in principle there should be a dot if you use the English version of origin, but because I'm using the German version, so in this case I have replaced all the dots with a comma. Now we can import this, as I have also explained it in one of the previous videos, but here in this case I want to show you another possibility. You can actually, in this case it's very simple, you can simply select all of them by pressing Ctrl A, and then you can go to origin, go to the first row of the first column, and then press Ctrl V, and then you can directly copy all the data. And you can see that now everything is inserted, 100,000 rows in total. So what we have to do now, or what we can do now first, is that maybe creating a histogram from that. So we will select the first column, and then we can click on draw. And I have done this already previously for testing purposes. If it's not shown here in your last used one, you can actually just simply go to statistics, and then you can even choose here different distributions, different type of diagrams that you want to create, maybe a box diagram and so on. But in this case, as I said, we want to talk about histograms. So we can click here on histograms, and when you see it automatically creates this very nicely shown histogram, where we have here our mean value around 5, as I said before, and the binning of course is arbitrarily created by origin. One can also change that, but in most of the cases it's already good as it is done automatically. And here we can see the count rate, so the number of entries per bin actually. So everything is in principle self-explained, so to say, so we don't have to do anything. In this case, unfortunately, we cannot make directly a fit to this histogram. We have to do some more tricks in order to achieve that, but nevertheless, we can let this open for testing purposes. And now what we can do, we have already selected the first column. In the next step, we have to click on actually statistics and then on descriptive statistics. And this we have to do in order to create a frequency count. And this we do by here going to frequency count, in German it's Häufigkeitenzählen, and then I have done this already before, so if you have done this you can click on last used and it will just do the same again. But as you might have not done this before, you can click like me on dialog open or open dialog, and then it automatically inserts everything which is important. This is the data which is included. And then there would be the possibility to also change things manually. But as I said, most of the time the automatic processing of origin is already good enough. So in this case, and maybe I can also go into that in another video if you are interested in this, you can write it into the comment section. But for the time being, we will just keep it as simple as possible. So what we can do now is just pressing here OK. And now you can see you get a new sheet, a new table, where you get the values that are actually counted. So in this case, the smallest one is something around 2.9, and the highest one is around 7.1, which makes also sense. Maybe if you create a much higher statistics, you would also get values smaller or larger than that. Of course, it would be go until infinity, but due to the limited amount of statistics, it will start here at 2.9 and 7.1. Okay. Then we have here then, or this column we can actually ignore. What would be important is here this count rate, similar to what is also shown here in this histogram. And you will see that the number of entries that we have in this histogram equals the number of entries that are shown here in the third column. So this is consistent. And also we have here the cumulative count, which means that it adds up all the bins starting from bin 0 and goes until the last one. And in this case, then it would be 100,000, which means this last row in the last column shows you, in this case, how many entries you have in your histogram. And this can be also sometimes very useful. But now we want to actually perform that fit. And now we can do this very similar to what we have done already with functions before, because what we have now here is actually a function. We have here our x values, and we have here in this column our, our y value. So we have to actually press Control and then in this column. So now we can also plot this in the same way how we have done before in the form of a function. So what we can do is clicking on drawing. And then we have already created this dot graph before, or we can also use a line graph, of course, but here in this case, maybe it looks a little bit nicer. And when you compare these two histograms with each other, you will see that, or when you compare these two plots with each other, you will see that the histogram looks very identical to the one which we have now created in the form of a function. And now we have everything to really do our fitting. So what we can do now is click on analysis. And then we can click on fit and nonlinear fit. And again, we want to open a new dialog because we have not used that before actually. And then we could, of course, do the same what we have also done in the previous video. We could define our own fit function, which I would not recommend because in this case, it's not good to reinvent the wheel and use things which are already implemented. So we can check here in the origin basic functions, what kind of functions are already included. Now we could also do this last time for the polynomial, of course, but now we will really try that. So what we can do, we can try to take a look where the Gaussian could be included. And this should be already in the origin basic function, so we don't have to change the category. Now we can go to function here and see that indeed we have here two Gaussians. One is just called Gauss and one is called Gauss amp. And we can go here to formula to check where's the difference. So this is Gauss amp, where you just have an amplitude in front of our e function and in front of our exponential function, which is maybe the way how you have seen it before. You have an additional linear offset, which is also important. If you have background, then it just shifts your Gaussian up. But in other way, I would say it looks like a typical Gaussian. Or you can switch to Gauss, and then you will see it looks in principle identical to the one which we have seen before, with the difference that we have our normalized factor here, square root of pi divided by 2 times the standard deviation. This is actually included here, which is sometimes also beneficial. I usually like that one, because you have the normalized one, but if you don't want to have a normalization, you can go to Gauss amp, and then you will get the amplitude without a normalization. Or actually, then you get the amplitude including a normalization, and here you are getting it without. However, it doesn't matter so much because we are not interested in the amplitude. This is just giving you the number of entries, so to say, or the number of entries in the highest bin. What we are interested normally in is the center bin, this XC. I mean, not the center bin, but the center of our or the mean value of our histogram, XC, and our standard deviation omega in this case. So now the only thing which we have to do now, we have to go to calculate again and switch to auto. So everything is exactly the same how we have done it last time. We can also go here to example curve, and this is also very nice. In some cases for the basic origin functions, it's actually shown what it means. The standard deviation is this omega or this W, which is the typical sigma value for a Gaussian. Then you can also have a full width at half maximum, the area, and also the interval which is chosen. All that you can just check. And here you can also see the code, how the function is implemented. You could also set again some parameters here. You can set some offsets, and you can shrink the interval in which you want to fit, and so on. All that we don't want to do. So we directly click here on fit. And yeah, now you can see, first you saw that the curve was not actually fitting well because it took the initial parameters. And now after finalizing our fit, we see now here this red fit curve. Yeah, we can also switch here again to the parameters. We can see this here in our table, the fit parameters. We can also look into this table here where we can see the fit parameters. So XC, as I said, is the mean value, which is close to 5, exactly what I have also chosen when I generated the data. And W is close to 1. Yeah, and this is just because of different definitions of the sigma value in case of root and origin. Yeah, so this is perfectly okay. So we have here standard deviation of 1. And yeah, then we can also see here this A value, which is our amplitude, and this is 20,000. Yeah, in principle, we would expect a smaller value here because we have only a maximum of 16,000. But as I said, this has something to do with the normalization and the sigma value. Then pi has to be, square root of pi has to be included and so on. So there is a difference between the real amplitude and that one here, but this is just the normalization. And you can also get a look here at the chi-square value, which is significantly large. Yeah, but should maybe investigate from where this large value is coming. But I guess this is not the one, I'm not sure, but I guess this is not the one per degree of freedom. So you also have to divide that and then see that chi-square actually changes. And yeah, but the R value is very good. It's very close to 1. And this already shows that the fit worked well. Okay. Yeah, and then of course you can obtain much more things from that. But for the time being, I want to stop here. And if you have any further questions, please put it into the comment section as usual. If you want to see more about that histogram stuff and fitting, then also please write it into the comment section. Otherwise, if you like the video, please hit the like button. Please subscribe my channel if you have not done so far, and see you otherwise soon for a new video.